Okay, I see there has been an issue with sound, so I'm going to start back again. Um, Hi, I'm Manasa. I am a research faculty at IUCAA, and I am an experimental physicist by training, and I work on mainly my research interests are on lasers and optical systems that are used for precision measurement. And here at IUCAA, I'm part of the LIGO-India team, sharing responsibilities for the upcoming LIGO-India gravitational wave detectors. Today, I would like to dive into a little bit about the details of the instrument science and technology that goes behind building these gravitational wave detectors. Um, Okay, so as part of the lecture series, you've already heard a couple of talks regarding the instrumentation behind gravitational wave detectors. I will try to dive into a little bit of the details so that we can appreciate the instrument science and effort that goes behind building one such detector and why we call it a mega project. Um, so it all starts with, let me give a little bit of a background. It all starts when, with a definition of gravity, and as described by Newton's laws, gravity is actually a force. While Newton's laws were able to describe the effects of gravity, it still could not propose a mechanism as to how things worked. So then came Einstein with his general theory of relativity, and he called gravity as the curvature in space-time. He described gravity as a curvature in space-time. And for him, according to him, it's actually a fundamental part of the structure of the universe. And depending upon how the objects move and rotate within the space-time curve, you see twists and ripples and everything else that comes along with it. So if you're going to imagine a massive body in space-time curvature, as it moves around, it distorts the space-time around it. And if you would like an image of how that would look like, that is represented in this picture. And carrying this image forward, along with a very elegant expression to describe Einstein's equation given by John Wheeler. This helps to get a very clear image of what the Einstein's equations mean. Space-time grips mass, telling it how to move, and mass grips space-time, telling it how to curve. And because of this, whenever a heavy object or matter moves or changes its configuration, the gravitational field around it changes. And when this change propagates, it propagates as a ripple in the space-time curvature. And the ripples in space-time are what we call gravitational waves. So gravitational waves, like the electromagnetic spectrum, also can be put into a spectrum depending on the frequency of the wave. And the frequency chart that you see in here maps the frequency to the different sources that emit gravitational waves. And as you can see, for a particular frequency of the gravitational wave, we have a certain type of detector that helps us detect these gravitational waves. For example, if you see the phenomenon that the sources that we are looking at using ground-based interferometers are defined in the order of milliseconds or a few hertz to hundreds of hertz. And the events are binary neutron stars and binary black holes. The same way, we have other types of gravitational wave detectors that are space-based, or the pulsar timing array and the cosmic microwave background measurement. So these actually help us measure detect the different frequencies of the gravitational waves along the spectrum. And when it comes to building these detectors, we already have a few, and some of them are being proposed. And this chart shows us the detectors, gravitational wave detectors, and maps them across the frequency. And as you see, all the ground-based interferometers, for example, are LIGO detectors, the Virgo detectors, GEO. There's another one missing, that is the Japanese detector Kagra. So all these fall on the right-hand side of this plot, and they help us find sources or locate sources like binary neutron stars and binary black holes. If you want to build a detector, you should, to detect a gravitational wave, it's important that we understand the physical effects of a gravitational wave. So what we would start doing is like consider a ring of freely falling test masses and look at how it reacts to a gravitational wave propagating through it. And as you can see, when a gravitational wave moves across a ring of freely falling test masses, you see that the ring gets stretched and squeezed, and the way it gets stretched and squeezed depends on the polarization of the gravitational wave that propagates through it. Now, if you consider a Michelson interferometer, and you place the two end mirrors of the Michelson interferometer along the circumference of the ring of freely falling test masses that you saw in the previous picture, you can see that the arms of the interferometer get stretched, elongated, and squeezed in the same way when a gravitational wave passes by. So what happens in the Michelson interferometer is the length of one of the arms gets stretched and the other gets shorter. And this effect is very much visible as a phase difference between the light that propagates in these two arms and gets detected at a photodetector in the dark port of the interferometer. So if the light interferes constructively or destructively, that can be seen at the dark port of the interferometer. So if we have to look at, if we have a gravitational wave passing through a simple Michelson interferometer, and we consider a point wherein one of the arm gets stretched and the length difference that it produces is delta L, we have a parameter we can define a parameter called H, which is the strain in the Michelson interferometer. And this is the ratio of the length change in the interferometer arm over the length of the arm itself. And as you keep changing the length, you move through the bright fringe and the dark fringe of that can be seen at the photodetector itself. And when you put in the parameters for a binary neutron star, for a typical binary neutron star that we would like to detect into to find the strain that it would produce or the H that it would produce, you'll find that the H value is of the order of 10 minus 21. And this is a very small number, which is a challenge when it comes to using interferometer for gravitational wave detection. But the concept of using a Fabry-Perot for using a Michelson interferometer is flawless. So what you see in here is actually a concept, one of the very first conceptual documents that was put together to build the first two interferometers in the US, at Livingston and Hanford. What you see in here is a simple Michelson interferometer being proposed as not a detector but an antenna for detecting gravitational waves. And so, but a simple Michelson is not going to help us detect gravitational waves very easily, because as we saw, the H value that we need to be able to detect is very, very small. So we changed the configuration of the Michelson interferometer to make the detector more sensitive and be able to see these events. The configuration that we use right now with advanced LIGO, we call it the dual recycle Fabry-Perot-Michelson interferometer, or we call it the DRFPMI configuration. And what you have in this configuration is basically the arms of the Michelson interferometer being replaced by Fabry-Perot cavities so that the light gets more time to interact with the gravitational wave signal. And as well as there are a couple of recycling mirrors that are added, and these also work towards enhancing the sensitivity of the detector. So when you add additional components to the simple Michelson, you add a lot of components to the gravitational wave detectors in terms of optics, mechanics, and electronics to build a detector that can detect gravitational waves eventually. And putting all these together cohesively to work as a single instrument is a very big challenge. And one should understand that when we talk about improving the sensitivity of the detector, it is usually talking about reducing the noise of the components that make up the detector. In order to understand this in a little bit more detail, if you have a gravitational wave signal, which is shown by the red signals in here, if you look at the signals either in the time domain or in the frequency domain, if the noise levels from the components that make up the detector are large enough to mask the gravitational wave, it would become impossible for you to detect them. So what we would like to do is build components within the detector that have a much reduced noise level so that the gravitational wave signal becomes more prominent and detectable. So in terms of the gravitational wave, building the gravitational wave detectors, there are three components, fundamental components to the gravitational wave detector, as we've seen: optics, mechanics, and electronics. And the noise that they portray in the interferometer are in the form of displacement noise, optical noise, and electrical noise. As you can see, the optical noise comes from the laser as well as the optical elements that you used. The displacement noise comes from the mechanical suspensions, and the electronics noise comes from the data readout and how it is analyzed and controlled, and the control signals that come along with it. So when initial LIGO was proposed, or in any interferometer is built, we budget the noise levels of the components that constitute the detector. And when initial LIGO was proposed, target sensitivity was set up at 10⁻23 at 200 Hertz. And the relevant noise sources were all budgeted, and a total noise target was also set. And to put the detector together, it involved people from multiple institutions and multiple countries coming together and working for decades together till the first detection happened. If you look at the timeline for the detector, from the inauguration of LIGO in 1999, it took a few years before we reached design sensitivity and could have longer science runs. And if you look at this timeline on the sensitivity curve, you can see that the progress happened slowly over the years, and we were able to reach the design sensitivity that was proposed somewhere around 2006. And by then, while people were working towards progress in improving the sensitivity of initial LIGO technology, there was new technology available, and people wanted to take advantage of it but still reuse the facility in the vacuum system that we had. So advanced LIGO was already in the charts, and major upgrades were looked forward to. So the advanced LIGO detector configuration is what you see in this picture. And the basic design of advanced LIGO was very similar to initial LIGO, except for a few additional components. For example, the signal recycling cavity was an addition. But in addition to it, people have we introduced a lot other subsystems for better control, sensing, and diagnostics of the interferometer itself to up the duty cycle and become more useful. So in the iLIGO configuration, we have the main laser, which is a stabilized laser, and then it goes through some input optics which allow for stabilizing the frequency and the intensity of the laser. And the laser is then directed towards the beam splitter, which splits the beam into the two Fabricaro 4-kilometer arms. Apart from the two arm cavities, we have two recycling cavities whose length is determined by the position of the power recycling mirror and the signal recycling mirror. These are actually folded cavities. And from there, we also have at the output, we have the output mode cleaner, which basically filters off any other light in any of the higher order modes or in any other spurious light that comes from the sidebands, and those get filtered before it reaches the gravitational wave readout photodetector. So the way the whole system is put together, it's by assembling subsystems and bringing them cohesively together. So a LIGO detector can be split into subsystems, and I will go into the details of each of these subsystems just to appreciate the effort it takes to put the whole instrument together and be ready for detecting gravitational waves. So the first one is the pre-stabilized laser subsystem. In here, we have the light source and all the control systems that go towards stabilizing the laser in terms of frequency, pointing, intensity, and it has the laser itself, which is amplified. The power necessary to a higher output level of 180 watts is reached in stages. So we have the main laser, which is the NPRO non-planar ring oscillator, and its output is fed into a medium power amplifier, and then it's fed into a high power oscillator. So the PSL is designed to give high output power of 180 watt, but that is not the operating power right now when it comes to the operation at this moment. We are still operating at much lower powers than 180 watt. So along with that, the light source, we have other elements in the PSL. For example, the pre-mode cleaner in here. It is a bow tie cavity, and what this does is cleans the output from the laser of all the higher order transverse modes that can come along with it. We also have a reference cavity in here, and the reference cavity helps us in stabilizing the frequency of the laser. When it compared to the initial LIGO laser that we had used before, the iLIGO laser offers 10 times better intensity and frequency stabilization. And this laser was contributed by our collaborators in Germany. So when it comes to the real system, this is how it looks like. This is a PSL room at one of the observatories, and you can see how the whole system is being brought together. You can see the different stages, amplifiers in here. And Moving forward from the PSL subsystem, we then enter the input optics subsystem. And this is still not the interferometer. It still works as a conditioning subsystem before the light enters the interferometer. So in here, the main component is the input mode cleaner. As you can see here, the MC1, MC2, and MC3, they form the triangular cavity for the input mode cleaner. And the input mode cleaner itself is actually kept in vacuum, and the optics are suspended. This itself provides better stabilization of the PSL output in terms of frequency and intensity. So apart from that, the other components in the input optics subsystem is the Faraday isolator that that keeps the spurious light from entering back into the laser, and also serves as a sensor port for looking at the reflected signal from the interferometer. From there, we will move into the next subsystem, which is the core optics components. So the interferometer is made with optics, and the optical elements play a crucial role. The quality, the build of it makes a very crucial role in designing and putting the detector together. So the three main components that we worry about when we make these core optics are the choice of the material that is used, the polishing that they undergo, and the material that makes the coating on these mirrors. So depending on the performance that the optical element has to offer, different grades of fused silica are used to make these mirrors. And the polishing for these mirrors is also crucial, because while you keep into account the large scale uniformities, as you can see, some of these mirrors, the test masses especially, are like 35 centimeters. And while you keep into account the large scale uniformity, you also need to take care of the small scale smoothness that you achieve during polishing of these mirrors. And when it comes to coating materials, it is important that the optical parameters in terms of transmission and radius of curvature of these mirrors are very important, because even a few ppm change or a few percentage deflection from the transmission parameter leads to increase in thermal noise and scattering and mechanical losses in the mirror. So these parameters have to be follow a very strict guideline. And these, when it comes to how these core optics look like and how they have been handled and evaluated, you can see in here that a core optic mirror, the test mass weighs roughly around 40 kilograms. And we use specialized instruments like the ZIGO to look at the surface profile of these mirrors. And what you see in here is actually the image of the surface profile, showing variations of the order of few nanometers or less than that. And what you see in here uh, is the way the mirror is actually cleaned, because even small speck of dust or any scratches on this mirror could hurt us significantly. So the way the mirror is handled is by applying a polymer coat on top of it, and the coat is not removed during assembly, and that's the last thing that comes out when closing the vacuum chambers. So the next subsystem, now that the core elements are ready, they have to be aligned and brought together and positioned in the interferometer. So, and also the suspension subsystem should allow us to work with the different degrees of freedom and control the optics itself. So in here, depending on, again, the performance requirements for the optic elements, the level of damping that is required, the number of stages that of the suspension that is enables such a thing will be decided. For example, the test masses are the most crucial, and they come as quad suspensions. We also have some single stage, double stage, and triple state suspensions. Also, something that plays a significant role is the choice of the wire that is used to suspend these mirrors. For the test masses, there are few silica wires that are actually welded to these mirrors itself, and certain other mirrors actually use steel wires, wherein the thermal noise limits are still something that can be worked around. So what you see in here is a four-stage suspension that is being used for one of the test masses. As you can see, the red one with the red tinge is actually the test mass with the polymer coating on top to protect it during assembly. And what you see in here is the test mass, and then you see the penultimate mass, and then there are two other stages on top, which is steel blade springs that offer isolation and make a fourth stage quad suspension. The mirror is actually suspended using few silica fibers that are welded to the sides of these mirrors. And actuating on these mirrors, the mirrors are suspended, but you should be able to control and align the optics. And that is made possible by using electrostatic actuation, which is non-contact method, and keeps the noise levels at a lower end. So the next subsystem, you have these suspensions ready, but they have to go on seismically isolated tables where you can actually use active and passive isolation techniques to allow for the suspensions, to allow for damping of the higher amplitude motion that comes along with seismic effects. So the typical seismic isolation system is built of two types of stages. One is the one that is outside the vacuum, and we call it the HEPI, which is the hydraulic external pre-isolator. And there's one stage which is inside vacuum, which is the internal seismic isolation system, and this sits inside the vacuum. So what you see in here in the picture is actually a schematic and a CAD model of the HEPI and the ISI being used for two different types of chamber. One is the BSE, which is the basic symmetric chamber, and then we have the HAM, which is the horizontal axis, which gives horizontal access to the optics. So that is the HAM chamber. So the next subsystem that we will discuss is the auxiliary optics subsystem, and this subsystem has many more sections within it. And what this collectively provides is for additional sensing, diagnostics, and control of the interferometer. We will discuss each of it briefly. So, for example, when we talk about scattered light control, the components that come along with it are the in-vacuum baffles. So there is, whatever you do, there is still some amount of scatter that happens inside the interferometer, and to avoid the stray light interfering with your detector and adding additional noise, we put in vacuum baffles, and the material properties of these baffles are such that they can absorb the stray light which are interfering back, going back into the interferometer and showing up as noise. The other system that is used for monitoring the alignment of the detector is the optical lever. The optical lever provides a reference and also stabilizes the angular alignment of the optic. What it basically is a fiber-coupled helium-neon laser that falls on the surface of the optic and gets reflected to a quadrant photodiode. And depending on the position of the reflected light on the photodiode, you will be able to track and the angular alignment of the optical lever and use a control loop to stabilize it. So the next one that also comes under the auxiliary optics subsystem is the output mode cleaner. What the output mode cleaner does is it filters out anything that is not in the main laser beam that carries the gravitational wave signal before it reaches the photodetector. So this helps in drastically in reducing the power that falls on the power and all the unwanted light that falls on the photodetector that detects the gravitational wave. Also part of the auxiliary optics system is the thermal compensation system. So even though the mirrors are designed to have a few ppm of absorption, once you ramp up the laser power, there is still some heating effect on the surface of the mirror, which causes some surface deformation and gives rise to thermal lens effects. So what the thermal compensation system does, it uses wavefront sensors that look at the surface deformations of the test masses, and then it uses a combination of ring heaters. Here is the picture of the ring heater. It uses a combination of ring heater and a CO2 laser to project a heating mask on the test masses, which compensate for the heating, for the thermal lens that is formed by the main laser beam. So this is sort of adaptive control that is being used on the mirrors in LIGO. The also another auxiliary optic system which is important for the interferometer is the arm length stabilization system. So far, we've been told that these are the 1064 nanometer is the only laser that propagates in the interferometer, but we also use additional lasers for diagnostics. For example, you saw the CO2 laser that is being used by TCS. And now in the arm length stabilization, what we do is we have two additional lasers, auxiliary lasers, which are in green. You can see this is a 532 nanometer laser, which is half of the wavelength that the pre-stabilized laser emits. And these lasers are locked to the arm cavities individually. What this does is, if you compare the frequency of these auxiliary laser with respect to the second harmonic that is generated from the main laser, it will give us a reference to how far each of the arm cavity is in resonance with respect to the main laser. So this allows us to bring the arm cavities systematically to tune them in and out of reference with respect to the main laser. And the most important point is it allows for decoupling of the 4 kilometer arms from the rest of the interferometer. So next along the line of subsystems is the interferometer sensing and control. And this involves everything that allows us to sense and control the various degrees of freedom of the interferometer. And what does it mean by controlling the degrees of freedom? So if you want the detector to be in a very useful state, looking at gravitational waves, you want the interferometer to be at an operating point where you want the cavities resonant and the interferometer itself resonant to it. So all the subsystems that help in sensing the different degrees of freedom of the interferometer. For example, the length of the 4 cavities, including the arm cavities, the power recycling cavities, and the Michelson itself, whether you want to lock it at the dark fringe or offset it a little bit from the dark fringe, and then the global angular control of the interferometer. And along with that goes what the ambient noise, that is, for example, the temperature fluctuation from the center to 4 kilometers far away, the wind direction, and any other ambient noise effects that come from the interferometer. These all fall under this subsystem. And we use control loops that actually helps us to sense and control the different degrees of freedom to keep the interferometer at a locking point, or to acquire lock and then keep it at the operating point. So the controls and data system. So this subsystem is like one of the most important, because all the other subsystems, they are most of the they are in vacuum, and they have to be enabled with real-time digital controls. And this is the CDS includes standard interface electronics, computing, network, and all software tools that enable us to do real-time digital controls for the interferometer itself. And for LIGO, this data acquisition architecture is a custom-built one, because LIGO is the only one that uses this kind of an architecture. So all these subsystems that I told, they have come together over a period of time from 2008 to 2015, although I should say that the R&D started way ahead of 2008, while people were still working with iLIGO. And what this means on the noise plot is better sensitivity of the detector itself. So we were able to do better in terms of seismic isolation, thereby reducing the noise at the lower frequencies. With increased laser power and signal recycling, we improved a lot in terms of sensitivity for the higher frequencies. We improved thermal noise by changing the suspensions and the materials that we've been using for building the components of the interferometer. So when everything came together, and when the detector came together, we were able to make our first detection of gravitational waves. That happened 14 September 2015. And we are still not at the advanced LIGO design target as yet, but we have started making meaningful detections from then on. And at this point, I would like for everyone to note that the Nobel Prize that was given in 2017 was not given for the first detection of gravitational waves, but for 4 decades of effort that led to gravitational waves, which was led by 3 pioneers. So once we had the first detection, we never looked back, and we have been making confident gravitational wave event detections through our observation runs 01, 02, and 03. So we've also started, people are getting excited to do multi-messenger astrophysics, because for the same source, we are able to get complementary information, which is carried in the gravitational waves in the form of neutrinos, in the form of cosmic rays, photons, and all bringing in together more information about the gravitational wave sources around us. So what about the future of LIGO? We have to put a checklist and say, okay, these are the things that we've detected, these are the things that we should be looking for. Is that all about the future of LIGO? No, we have to think forward, and then keeping in mind that LIGO is not an imaging detector. If it was an imaging detector, just 2 detectors would have been enough, but LIGO is an antenna. As you saw in the first conceptual document, it is actually an antenna. An antenna comes with a pattern. So as much as these detectors are good for detecting a gravitational wave source, they're not so good by themselves if you want to localize these sources in the sky. So what the world needs is a gravitational wave detector network, and that's where the role of all the neighboring networks that we have on ground play a very major role, and LIGO-India, being an upcoming detector, also has a crucial role to play. So in here you have the already existing global network of detectors, which is the LIGO, and then we have the Virgo in Europe, and then we have Kagra in Japan, and we have the Geo detector in Germany, and LIGO-India will be joining this network. And the effect of a network of detectors is can be very much appreciated from this figure that you see in here. So as you can see, with just LIGO and Virgo, the localization for the sources of binary neutron stars is not that great. And you can see that once LIGO-India pitches in, there is a significant improvement in sky localization. And this is the need of the hour if we want to do multi-messenger astrophysics. Apart from sky localization and building a global network, people have been doing work in the background, and we should look ahead and start thinking of what the future holds for us for these terrestrial ground-based gravitational wave detectors. So if we look at the next 10, 15, 20 years, we see that we already have upgrades for the current facility as A plus and Voyager working towards these upgrades as such within the current facility. And also researchers, the community is working towards new facility called the Cosmic Explorer. And all these are going to actively happen over the next decade. And if you look at how much of an improvement we get by these new ventures that are in line, is that you see that O2 is actually the sensitivity of the advanced LIGO detector from the second observation run. And you can see that the upgrades that are coming up, the LIGO A plus Cosmic Explorer, they offer significant improvement in sensitivity. And what this translates in terms of the reach, astrophysical reach for identifying sources like neutron star mergers and then by black hole mergers, is that we will be able to detect more events as we improve the sensitivity of the detector. What you see in blue here is the O2 sensitivity, and we've been detecting already gravitational wave sources, but improving on the sensitivity of these detectors will help us see more events and reach farther in the sky. So what does this mean in terms of people in instrumentation and other disciplines of research? So these are the third generation of detectors that are coming up. And if you look at the timeline for these detectors, the conceptual right now at 2020, we are sitting at a conceptual phase for all the subsystems. For all the subsystems that I've described, we are at a conceptual stage wherein ideas are being pitched in, and a lot of R&D and a lot of investment has been going on towards R&D for these detectors. So with the upcoming LIGO-India detector on our own soil, the research community in India has to pitch in and show our contributions to the global community in terms of building the next generation instruments in terms of upgrades that they will undergo in the next decade. So when it comes to looking at the sources for gravitational wave and opening up a new field of gravitational wave astronomy, it is rightly said that LIGO-India is a mega project because of the efforts that have gone in over a span of few decades. And it does not stop there with the detections. There is far great excitement that comes along with venturing into the research and development that we look into for the future in making this more meaningful and exciting. So we can have some questions on this. I'm going to So we will take up some questions. So, okay, I'm going to take some detector-related questions. So Sarah Satpathy asks, how can we say that the vibration isolation platforms can keep out seismic waves, but not gravitational waves that are so much smaller in amplitude? So as you can see that when I first showed how an interferometer is being affected by a gravitational wave, if you would want to see the effect of the gravitational wave on freely falling test masses, and our design efforts are towards making the test masses that we've used in the interferometer to obey a freely falling object, and which is why all the other systems support systems are necessary, so that they are isolated from the rest of the environment. And the vibration isolation platforms as well as the suspension system work towards enabling that. Manisha Panigrahi asks, instruments built on a large scale require sophisticated techniques to maintain and repair them. How do you ensure that each component of LIGO is working effectively in real time on a day-to-day basis? So we have when it comes to maintaining the detector, each detector is staffed with manpower that keeps monitoring the parameters of the detector when it is in observation mode. And when things drift far off or we see something that is failing, that's when the duty cycle of the instrument falls off, and then that particular component is replaced if it can be done without opening the vacuum systems and things like that. So it is being monitored all along, and that is what the people who are working for the detector at the detector sites do. They're all people who are scientists who are trained to look at the different subsystems and keep track of the health of each of the subsystem that we're using. Anil Rajapattamahuni asks, what is the time scale over which the strain occurs? So the time scale of the strain depends on the frequency of the gravitational wave that you would want to detect. So as we saw that the gravitational waves come in different frequencies, and most of the detections that we see happen over a few hundred hertz to kilohertz along those uh, frequencies. And if you recollect the plot where we saw the gravitational wave signal and the noise plot of the interferometer, you see that a gravitational wave signal comes at all frequencies, because these mergers are events that actually like ramp up in time, which is why you hear there is an increase in frequency as you get closer to the merger. So that is what the strain plot for a gravitational wave would look like. Sribala asks, why is the high power amplifier not directly used instead of the other two stages? So when it comes to building a laser, you cannot design one particular, if you want to ramp up to powers of the order of a few hundreds, it cannot happen in a single laser, and always happens in stages, because you have solid state elements along the way and thermal issues. So the first stage might not require any sort of cooling or cryogenic cooling, but the later stages, as the power amplifies, you would start having the need for cryogenic cooling. And which is why whenever you ramp the power of the laser, it always is stepped up in stages and doesn't happen as one whole system delivering 180 watts all of a sudden. Karthikeyan asks, what type of laser is used? I'm not sure which laser you're talking about, but I'm assuming that it is the main laser. And the main laser is actually a neodymium crystal that is cut. It's a non-planar ring oscillator. So the crystal itself is pumped and made to lace. That is the start, where you get 1064 nanometer light out. And then next stages actually amplify this. So you have first the medium stage amplifier and then the high power amplifier that delivers at the next stage. So it's a custom built laser, which means that the laser is homemade by our collaborators in Hanover. Okay, next question. What information can we get by observing the gravitational waves emitted by any astronomical body? So we already have, so whenever we announce a gravitational wave event, the two parameters that our people are looking for is the mass of the objects that come together and the type of the gravitational wave decay that we see. And those are crucial parameters that tell about the event in itself. And the time scale of the event is something else that is very crucial. And how the waveform rings down also gives us information about the event source. If I'm not sure. Harsha Mehta asks, if two black holes merged in a nearby solar system, would we still need a very high sensitivity of detector to detect the gravitational waves from this event? Uh, so um, so the strain levels of the gravitational wave source, the gravitational waves we produce on our interferometer, at least the known sources around us, is of the order of 10 minus 21. And those are the sources that we are sensitive to. If we have to imagine a source that is very close to us, you know that gravitational waves decay over distance. So if we have a source, imagine, just for imagination, if you have a source very close to us, we would see, depending on the distortion that it would produce, we would be able to pick it up through our gravitational wave detectors. Karthikeyan asks, what does ITM stand for? ITM stands for input test mass, and ETM stands for end test mass. So LIGO uses a lot of jargons, and I've tried to be as explanative of them as possible. I only took that for granted because there were previous talks which talked about this. So we have the beam splitter, BS, we have PRM, which is the power recycling mirror, and then we have SRM, which is the signal recycling mirror. So these are the main core components of the interferometer. All bodies in the universe are drifting away. Can these bodies produce gravitational waves? So this is it, so to answer this question, like any heavy body that moves produces produces a change in the field around it, and it does produce gravitational waves. For example, if we have to look at the motion of sun and earth, the earth moving around does produce a gravitation, does produce a walk around it, but that is very, very tiny when it is compared to, if you work out the numbers, that comes down to even tinier numbers than what we've worked out for really dense matter like binary neutron stars and binary black holes. Because binary black holes and neutron stars are really dense masses, and to see a significant warp in the space-time, it is necessary that the masses that we're talking about are dense enough. And We should be able to see gravitational waves whenever any massive object moves or drags itself or goes around. You should find ripples or twists and turns whenever this happens. Abhishek Kandelwal asks, how are gravitational waves polarized? Are there other types of polarization of gravitational waves apart from plus and cross? So gravitational wave is a quadrupolar wave. And if you work out the solutions for the quadrupolar wave from Einstein's equation, the only allowed polarizations are the plus and cross, and those are the polarizations that our interferometers are sensitive to as well. So I think I've taken questions. So following this, we will be still continuing our GW at Home lecture series, and the lecturer for the next talk will be Dr. Sendil Raja, and he's from RRCAT. He leads the one of the groups that is going to build LIGO-India from RRCAT. I am sure that his talk is going to be interesting, and you will all tune in again to listen more about it from the safety of your home. Thank you. Stay safe.